Welcome. Today my team and I will be presenting how Gauss law applies onto a long uniform line of charge. I will start with explaining what a charge is and the electric field line surrounding it. Arindam will then explain what an infinity line of charge is and which Gaussian surface would asymmetrically enclose it. Lastly, Yusuf will derive the final formula and compare the Gaussian surface chosen to the one that includes a point charge. So let's start by the definition of what's the charge. Charge is a physical property of matter that repels each other when the same type of charge exists and attracts when the charges are opposite in the interaction object. The SI unit of the electric charge is the coulomb denoted by C. The principle of superposition states that every charge in a space creates an electric field at a point independent of the presence of other charges in that medium. This electric field can be visualized with electric field lines showing its direction and strength at different points in space. We can remember the field lines by three rules. First one, the field lines are tangent to the direction of the field at any point. Second one is the field lines always start from positively charged objects to negatively charged objects. The line must never cross. For example, the charge shown here is positive as the electric field lines point outward, and the charge shown here is negative as the electric field lines point towards the charge. The field line describes the vector of the electric force outputted on a positive charge placed in that point in a space. We can figure out how strong that field is if the lines are closer in that area.
In this presentation, we were given the task to apply Gaussian law on an infinite line of charges. Before going to Gaussian law, we need to understand how the electric field lines work in an infinite line of positive charges. In case of an infinite line of charges, the perfect symmetry of the line causes the horizontal field component to cancel out. The only part that does not cancel out is the radial component, which points directly away from the line. As a result, the electric field lines form a uniform radial pattern around the line, spreading outwards in all directions but never bending sideways. According to Gauss law, the total electric flux through a closed surface is directly related to the charge enclosed within that surface. The law asserts that if a surface maintains the symmetry of an enclosed charge distribution, the integral yields a net electric field determined solely by that enclosed charge. This is how it is denoted mathematically. A cylindrical surface is the best choice because it matches both the radial symmetry and the lateral symmetry of the infinite line of charges. The field spreads outwards equally in all radial direction and it is the same along the entire length of the line. This match in symmetry makes the calculation with Gauss law simple and accurate. Electric flux measures how many electric field lines pass through a surface. It depends on three factors: the electric field, the field strength, the surface area, and the angle between the field and the surface normal. At theta equal to 90, flux is 0. At theta equal to 0, the flux is maximum. Since the field lines are parallel with the phase vector of the cylinder, we have to consider the area of the curved lateral surface as explained before. dA is infinitesimally small, but added up equals to the curved lateral surface of the cylinder. Radial symmetry ensures the equal values for electric field strength across the whole cylinder. However, for the faces of the circle on the end of the cylinder, the field lines are perpendicular to the phase vector. Therefore, we don't consider it in our final equation.
Considering the factors that my team members introduced onto Gauss's law would mean that the sole contribution to the total outward flux arises from the lateral curved surface, where E acts radially outwards. The lateral symmetry of a line charge allows E to possess the same magnitude everywhere on the lateral surface. Thus, the radial electric field exhibits the characteristic dependence of E equal to approximately 1 over R. Having derived the electric field caused by an infinite line of charge, a direct comparison with the field of a point charge provides some insight. The Gaussian surface that encloses a point charge is a sphere, as it respects the symmetry of the point charge. The electric field of a point charge diminishes as the inverse square of the radial distance. That is the case due to the difference in formula between calculating the surface area of the cylinder and the sphere, which is highlighted in blue. This exponential contrast is significant. The radial proximity at which the electric field from a line charge retains a substantial magnitude is much greater than for a point charge. In conclusion, Mahshid began by describing what a charge is and the electric field lines around it. Arindam then discussed the concept of an infinite line of charges and identified the appropriate Gaussian surface to symmetrically enclose it. Finally, I derived the resulting formula and compared the chosen Gaussian surface to the one for a point charge. E is equal to lambda over 2 pi epsilon 0 times r. This expression substantiates Gauss's law as an effective analytical strategy for charge configuration exhibiting cylindrical symmetry. We hope this explanation helped clarify the application of Gauss's law on a long uniform line of charge using a cylindrical Gaussian surface. And thank you for watching.